Hi, I'm Beth Faber from the Hydrologic Engineering Center, and this is part 2 of the lecture on uncertainty in frequency estimates. This is the 8th lecture in the statistical methods in hydrology class. So in our list of topics, we're now going to talk about contributing factors, right? And this video will go as far as talking about sampling distributions. So contributing factors, you already saw these in the lecture on parametric modeling by Mike Bartels, so I'm going to go through them fairly quickly. Measurement error, how well are large flows measured? So I think anything that Mike Bartels said to describe measurement error probably would be better than what I would say here. So refer back to what Mike described in the parametric modeling lecture. The second factor, model error. Okay, for example, does the log Pearson type 3 distribution really describe the annual peak flow frequency well, or would some other distribution do it better, right? Also, not just what the model is, but what method is used to estimate the parameters, okay? So let's look at some possible error from the choice of model, or more like, let's look at some uncertainty from the choice of model. So here is a record of annual peak flows. We're showing the plotted data versus plotting positions on a linear axis here, and a histogram of linear stream flow. And then on the right, we've got the same data plotted on a log axis and a histogram of log flow, all right, both on a normal probability axis. So fitting a selection of different frequency curves to this data, we see a lot of difference. Now, some of these don't make sense at all, right? Let's see, it's the Gumbel and the normal distribution go negative. So those are obviously not good choices, and they don't fit in the middle or at the top either, right? But the others are all reasonable, and we can actually see that most of the distributions give about the same result in the middle and the low end, so the middle and the low end of our data. Where they really differ is up at the top. And it's up at the top that we really care the most, right? We're interested in estimating the low frequency events of our extremes, right? And so we want low frequency extremes, then any choice of the model for fitting the data is going to have an influence on what we get as an estimate of the extreme upper tail. So the last factor is sampling error, right? Error in the estimates of distribution parameters due to limited sample size, causing an unrepresentative sample. That's what we just spent a lot of time talking about in the motivation section in the first video, right? This is the primary factor that we quantify in describing the uncertainty in our frequency curves because it kind of outweighs most of the others. So when we draw confidence intervals, they're generally based on sampling error. So I'm going to go on to describing or quantifying sampling error, and I'm going to start by talking about sampling distributions. Normally, if we were having this class in person, I would be asking everybody who's familiar with sampling distributions, and usually there's only maybe 5 to 10 people in class who've heard of them. So I'm going to proceed as if this is a somewhat new idea. So a sampling distribution gives us a description of the uncertainty in an estimate of a population value from a sample of size n. So not surprisingly, I like to study sampling distributions using Monte Carlo simulation. Right? So like the 1,000-year record, which we looked at as many 100-year records and 50-year records, and like the six-sided dice in the introductory lecture, we can study the error in estimating probability from a small sample by estimating probability from a small sample from which we know the original probabilities, right? So if we start with the known distribution, we can randomly generate small samples from it of size n, and we can make whatever estimates we need to of moments or probabilities and do that many, many, many times. And because we know the original distribution, we know the right answers, right? So we can see the error in each of those estimates, which we can then make into a distribution and describe. So with the six-sided dice, we looked at estimating probability based on relative frequency. And with the 1,000-year record, we looked at estimating the 1% flow. But originally, we looked at estimating the mean, standard deviation, and skew. So, right, all of those things are things that have sampling distributions that we can address by estimating them randomly with Monte Carlo simulation from limited samples. Right, so we're looking at estimates of distribution parameters or moments. For many distributions, the moments are the parameters, but for some they're not. And then estimating probabilities or estimating quantiles like the 1% event. Okay. Now we're going to start by talking about properties of estimators. Okay, so we're going to delve a little bit into statistical estimation theory. That theory provides some criteria for selecting estimators of population values. We're going to talk about consistency and unbiasedness, right, as the criteria that we're interested in. And we're going to use the estimation of the mean as an example to work through. Okay, so first of all, there's consistency. As the number of observations becomes very large, the estimated value approaches the population value, right? That means that the estimate gets better as the sample size increases. And we said that a lot of times in the introductory lecture, right? A lot of our estimators are consistent in that they get better with a bigger sample, right? The other criteria that we're interested in is unbiasedness, right? Meaning has no bias. So for this, the expected value of the estimator equals the population value. Okay, so even with a small sample, the estimator doesn't have any expected error. It doesn't mean it doesn't have error, but it has no expected error. It means that the estimator is aiming at the right target. Okay. So consistency and unbiasedness are the things we'll look at in our estimators. And let's look at a real quick example of when we have consistency and when we have bias or not. All right, so for an estimator of the mean, on the left, equation 1 is just the sample average. All right, and this is a consistent estimator for the mean, gets better as the sample size gets larger. On the right, we have another consistent estimator for the mean. Right? It's not really a sensible estimator for the mean, but it is consistent. All we've done here is we've subtracted 9 from the sample size on the bottom. Okay, that's not necessarily a sensible thing to do, but we can see that even if this was our estimator, as n gets larger, this subtraction of 9 gets less and less relevant. And so as n gets up into 100, 1,000, 10,000, the minus 9 has less and less impact. So it is still a consistent estimator because it gets better as the sample size gets larger. However, this estimator is biased in that it is always an underestimate of the mean. It's aiming at the wrong target. Okay, so number 1 is consistent and unbiased. Number 2 is consistent but biased. And an example of an inconsistent estimator of the mean is the average of the largest and smallest values, for example. That wouldn't necessarily get better as the sample size increased. So creating a sampling distribution. Here's where we proceed with the Monte Carlo simulation. Right? We're going to consider a sample for the mean. We're going to use the sample average, our unbiased estimator, and we're going to create samples of size 10. Right? So we start with a known distribution. Right? Here it's a normal distribution, mean of mu, standard deviation of sigma. Right? And we're going to generate 10-member random samples. Right? Here we do it 100 times, but we can do it thousands of times with Monte Carlo simulation. Right? So for each 10-member sample, we compute our estimate of the mean. When we've done it many times, in this case 100, we make a histogram of that output. Right, in pink is the histogram of all my estimates of the mean from sample of size 10. Now, because this is an unbiased estimator, that means the average of all the estimates is going to be the population value, right, sigma. We're going to get it right after we do it many, many, many times. Right, that doesn't help us when we're only doing it one time, but right now we're just studying the properties of any individual estimate by looking at many estimates. Right, now this histogram of the estimates of the mean can be approximated by a normal distribution, and this is because of something called the central limit theorem. Right, the central limit theorem says that the sum of IID random variables will approximately have a normal distribution, regardless of what the underlying distribution is, right? So IID means independent and identically distributed, right? So the sum of identical, independent, and identically distributed random variables will have a normal distribution, right? And the larger the sample size and the closer to normal we are, the better that normal approximation, right? So the sample mean is the sum of identical random variables. Note that each member of the sample being drawn from the same probability distribution is then itself an identical random variable. So we're summing up identical random variables, and so the central limit theorem applies. right? So the distribution that we just saw as a histogram a moment ago is now going to be a normal distribution instead because of that approximation. And its mean is going to be at the sample, the mean of the original probability distribution. Its standard deviation won't be, obviously, the standard deviation of the original sample, right? The standard deviation of our estimate of the mean is going to be sigma from the original distribution divided by the square root of n, right? So divided by square root of our sample size. So meaning as our sample gets larger, our standard error in our distribution of the mean is going to get smaller. So let's look at it just with a larger picture. This is our original distribution that we're drawing our random samples from. And our sampling distribution of the mean, meaning the distribution that we can build by repeatedly randomly sampling 10-member samples and estimating the mean, is going to look like this pink distribution, right? It's going to have the same mean. Its standard error or standard deviation is going to be sigma over square root of 10. Right now, as we might expect with a larger sample, we're going to get better estimates of the mean, right? Square root of 10 is from a sample size 10. It's going to be over square root of 50, for example, if we had samples of size 50. So the whole thing would be narrower, right? So here's my sampling distribution in orange for a sample of size 50, right? Still normally distributed, but now narrower because sigma equals square root of 50. Now, let's take a moment to notice that these two normal distributions in the middle are quite a lot taller than our original normal distribution in blue, and that's because these are all PDFs, and therefore the area under all of these density functions is 1, right? So if we make it narrower, we have to make it higher, right? Not really an important point, but something to just notice, okay? So I'm going to show a demo of sampling distributions in a spreadsheet that I'm hoping might make that a little bit more clear, okay? So here's an Excel spreadsheet that has the base population frequency curve that I'm going to sample from, the PDF and the CDF in our traditional form are down here. I'm going to be sampling from a normal distribution. Up here, I have the distribution shown in a frequency curve form with the normal probability axis on the bottom, and a normal distribution on a normal probability axis is a straight line. Okay. On this next tab, I'm going to show estimating the mean from samples of size 10 and samples of size 50. Right, so our population statistics are over here on the top. The mean is 3.6, the standard deviation is 0.5, skew coefficient is 0 because it's normal. And now here's my sample of size 10. So here are my 10 uniformly distributed random values between 0 and 1. This uses Excel's rand function. Here are my log flows. Here are my flows, but my mean of logs is here at the top. Now, over here on the right in orange, I've got my sample of size 50. So I've got my first 10 random values, which are the same as my sample of size 10, and then I've got 40 more values, right? So this is going to be a full sample of 50, and its average up here. Right. So if we look on the figure, we see the original distribution PDF in blue. In these pink dots down here are going to be the values of my sample of size 10. The height is not important. It's just isolated to show you my 10 random values. And then my sample of size 50 in orange is on the next line. Right now, the average, the sample average of my 10 is the pink line. The sample average of my 50 is the orange line. So as you can see in this first sample, the sample average of my 50 values is much closer to the actual population mean than the average of my 10 pink values, right? Which there its mean is a little bit farther away. So the idea here is to randomize the process and to look at many different samples. So I'm going to hit F9 to resample from the spreadsheet. And now I have a different sample of 10 and a different sample of 50. And the sample averages as estimates of the mean are now over here in pink and here in orange. Each time I hit F9, I'm going to get a different sample and a different estimate of the sample mean. Right, I'm going to go through a bunch of different estimates. Occasionally, the estimate from the sample size 10 was closer. Here's one where the sample of size 50 actually got it exactly right. Right, here's a few more. Here's one where they actually give the same estimate. right? But if we go through a lot, we'll see that the sample of size 50 tends to be closer than the sample of size n. Rather than having to keep track that way, though, I went ahead and simulated each of the estimators from a sample of size 10 and a sample of size 50. I estimated each 1,000 times, right? So on this tab, right, so here in pink, we're seeing a histogram of 1,000 estimates of the mean from a sample of size 10, and in orange, we're seeing a histogram of 1,000 estimates of the mean from a sample of size 50. Right, and over here we've got the same two histograms plotted on the original distribution. So this is a depiction of the figure that we saw in the slides, but we can see a little bit more information, right? So if we come to these two columns, the first column is n equals 10, the next column is n equals 50. Here's my actual mean. Here's the average of my 1,000 estimates from the sample of size 10. And notice that the average of my 1,000 estimates from a sample of size 10 is just about the right answer, 3.601, right? That's because it's an unbiased estimator, so it's right on average. Right, here's my standard deviation of the estimates, and this is about equal to sigma over square root of n. Right, so this is the expected standard deviation or standard error of my estimates. Same for sample of size 50, right? And finally, the skew coefficient is fairly close to 0 for both of these because they are approximating a normal distribution. Okay, so let's go back to the slideshow. Okay, what if the distribution of x isn't normal? Remember, the central limit theorem said that the distribution of the sum of identical random variables is normal regardless of the underlying population, right? So let's just run through real quickly. When the original distribution of x isn't normal, we pretty much have the same situation, other than the fact that the central limit theorem doesn't apply very strongly when n is equal to 10, and it applies a little bit more strongly when n is equal to 50. Okay, so we're going to do the same experiment of 10-member random samples. Taking the sample average from the 10-member random samples, we're going to get a slightly skewed distribution of the sample average for n equals 10, right? Because the n being less than 30 is not quite strong enough for the central limit theorem. But the standard error of this distribution is still equal to sigma over square root of n. So if we look at this on the larger figure, here we have our slightly skewed distribution of flow, our random variable x to start with, and our sampling distribution for the sample average for sample of size 10 is still a little bit skewed, but once we get up to n equals 50, now we're symmetrical on this normal distribution because the central limit theorem does apply, right? So our sampling distribution for the estimate of the mean using the sample average is normally distributed for n equals 50. Okay? So here's a bit of a summary of what we just did. We are trying to build a probability distribution around an estimator for a value from another probability distribution. So I know it gets quite confusing to be talking about the mean of the mean and the standard deviation of the mean, but what we're really talking about is probability distributions around parameters of probability distributions, right? So for the sampling distribution of the sample mean, we saw that it was unbiased. So its own mean is going to be the population mean. Its own mean is going to be the value it's trying to estimate, right? So the mean of the mean is the mean. Okay, that one's a little bit silly, but the distribution of the sample mean does center on the actual sample mean. The standard error, or sigma, of the sample mean, we said was equal to sigma over square root of n. That's the sigma of the original distribution over the square root of n, right? So it gets better as the sample size increases. And the more variable the original distribution, the more error we're going to have in the estimate of the mean. And the less variable the original distribution, the less error we're going to have in the estimate of the mean. So we did say that when x is normally distributed, then the sampling distribution for the mean is normal regardless of the sample size. But when x is not normal, the central limit theorem says that the sampling distribution is only normal as n goes to infinity. Right? Now let's move on from the sample mean to the sample standard deviation. right? There's a sampling distribution for the sample standard deviation as well, right? So our estimate of the standard deviation has a distribution. That distribution has a mean, and it also has a variance, right? So the standard error of my estimate of the standard deviation is actually very similar. It's equal to sigma over the square root of 2n, right? The sampling distribution for the skew coefficient, right? It has a standard error equal to something a lot more complex, but which is proportional to 1 over the square root of n. And finally, the sampling distribution for relative frequency also has a standard error that is proportional to the square root of n. So it's kind of a general statement that the standard error of the estimates for parameters and for moments or for probabilities is proportional to 1 over the square root of n. Right? That's a very important result. All of those estimators are consistent, meaning they get better as sample size gets larger, but to reduce the error to half, you have to increase the sample size by 4. Okay, so this slide gives us kind of a summary of what we just talked about and tries to capture sampling distributions. I don't know if it's a clearer way, but we'll try. So across the top, we have 3 different population parameters or moments that we might be estimating: the mean, the standard deviation, and the skew, and the estimators that we might use: sample average, sample standard deviation, sample skew. And then what we have going down is the sampling distribution, how good the estimators are as described by the sampling distribution. So we just went through the first column, right? We found that the mean of the estimator for the mean is unbiased, and so it is the actual population mean. And we found that the standard error of that estimator, so how wide the estimate of the mean is going to be in terms of the sampling distribution, that's going to be sigma over the square root of n. And then we also saw that that sampling distribution for the mean was normal, and so the skew is 0. Right? We did the same. We looked at the same for standard deviation to some degree, and we know that the standard deviation is an unbiased estimator, so its mean is going to be at sigma, and we saw that the standard error was sigma over 2n. Right? It's not normally distributed, so the skew coefficient varied. The situation in the third column for skew is not as nice, right? It is actually a biased estimator if we look at the product moments. We did see that the standard error was proportional to 1 over square root of n, and the skew coefficient, the skew of the distribution of skew varies, and we will see that in the next lecture. Okay, so that is the end of video 2, and in video 3, we're going to move on to confidence intervals.